What's up, guys? So in this video, we're going to talk about the commutative, associative, and distributive properties, and more importantly, we're going to talk about why we like them and why we care about them. So if you've never watched my videos before, I highly recommend you pause and try the examples when prompted, and there are always free guided notes available at divideandconquermath.com. So here's where I want to start. So let's say that you've got your math and your English homework, and they're due on the same day at the same time. So here's my question. It doesn't matter which one you do first. So you might have like a preference, but it doesn't actually matter, right? As long as they both get done on time, that's all that really matters when you have a due date. So this idea that, in this situation, the order doesn't matter, this is the idea of commutativity. So now I'm going to show you what this law actually is. So we have the commutative law for addition. So let's see if we can apply the same logic to this. So you're going to let A and B represent any two real numbers. So then A plus B, so using that same logic from before, what would A plus B have to be equivalent to? Well, since the order doesn't matter, it would also mean that this is the same as B plus A. That's the idea of commutativity in math. And we also have this for multiplication. So you can see it's almost the exact same thing, except now we're just multiplying the two things together. So A times B would equal B times A as shown. Okay. So if I wanted to use commutativity, so let's say that I want to rewrite a couple of expressions using this law. So for instance, 3 plus y would equal y plus 3. So you can just flip-flop the order. Now, for b here, this might look a little bit awkward, but we know that this is 2/5 k. This really means 2/5 times k. So if I wanted to reverse the order, it would look a little awkward, but we could totally write it like this. Okay, so that's the idea. So I want you to think about these two, and D in particular I want you to be careful with. Maybe pause the video for a moment and just think about how to rewrite these. Okay, so for C, this will just be C times 3. 3C is the same as C times 3. Now, I talked about the idea of commutativity for addition, and it looks like I just gave you a subtraction problem. We actually can use commutativity here if we think about this in a slightly different way. So 2 minus z is the same thing as 2 plus negative z. Subtraction can be totally turned into an addition problem as shown, like here. And then you can use the commutative law. So to do that, then I would rewrite negative z plus 2. So the z has to stay negative no matter what. But if you keep that in mind, you can, in a way, apply commutativity to something that looks like a subtraction problem. Okay, so now let's switch gears. So you are buying chips, a drink, and a notebook. So here's the question. Does it matter which two items are rung up first when you go to the cash register? So once again, no, right? We know that it's going to be the same amount of money no matter what order you ring them up in. So this idea here, that it doesn't matter which two go first, this is the idea of associativity. So we have this law here for addition and multiplication once again. So now I'm going to introduce three letters. So I've got A, B, and C. So these are three real numbers. So notice what this is saying here. So I'm just adding everything up, but I've decided to group up A plus B first. Now, if I'm thinking about the example we just talked about, how would associativity apply here? Well, instead of bringing up A plus B first, what if I decided to do B plus C first? So this idea of associativity is if you're just adding everything up together and you want to group things up, it doesn't really matter how you group them up as long as you're just adding everything. And then we also have the same, or a similar law, not the same, for multiplication. So now I've got A times B, so grouping this together, times C. And once again, I can just kind of move where the parentheses are and change how I'm grouping it up. Okay, so let's rewrite the next two expressions using associativity. So I want you to kind of start thinking about this in terms of, if you are just given an expression that looks like this, you are allowed to apply associativity to it. So in this case, if I wanted to, I could do 4 times x first and then multiply the z, or I could do the x times the z first and then multiply by the 4. And if you wanted to get even more creative with this, you could also start flipping the order around. That would be the idea of commutativity with associativity. So that's something you can totally do. So this is something you're always allowed to kind of apply as long as you're multiplying everything together. If you've got division in there, then that kind of messes things up. And like I said, you can also do this for addition. So 2 ways I could rewrite this. So I could group up like this. This would work. Here's one way I want to group this. So now I've got 4 terms here. But I can still put the parentheses really anywhere that I want. So I could do the parentheses like this. Or if I wanted to, I could just do like one set of parentheses. So I could do something like this. So now I've just got the one set of parentheses right here in the middle. So the point is, if there's a way that you want to set up the parentheses and add things up first, you are allowed to do that as long as you are either just multiplying or just adding. Okay, so there's a bigger point with this. We like these laws because they make it easier to do mental or by hand calculations, which if you may have noticed that in the last example we were just working on. So thinking about this particular example, so in general, I think that people tend to notice tens faster when they are adding them up. So if we are thinking about this from the standpoint of the order of operations, the order of operations would say just to add from left to right. And so think about that. If I did that for a moment, so that would be, this would be 10 and then plus 3 plus 7. And then I would do this, so then this is 13 plus 7, and then I would add that together to get 20. So that takes a lot of time, and so it's maybe just not the most efficient way to go about this versus if I went, so let me clear this out. So the other way that I could do this that would make more sense would be to say I'm going to add the 2 and the 8, and I'm going to add the 3 and the 7. And I know that that's 10 and 10, so then that's 20. So you just get a much faster calculation if you apply associativity or commutativity in the right spots. So that's kind of why we like these laws, is they give us some power to make certain calculations simpler. Okay, so here's another example. So maybe you want to pause the video here and just try to rearrange this, and I would say use commutativity and associativity for this one. So notice everything is being multiplied together. Hit pause and then play when you're ready. Okay, so thinking about this, the order of operations would say that I have to do the parentheses first, but now that I have the commutative and associative laws and I see that I'm just multiplying, I know that I'm allowed to actually rearrange this. And what I want to do actually is I want to put the 1/5 and the 10 together because I know then the denominator will cancel out, just like I want to put the 1/3 and the 6 together. So I'm actually going to rearrange this whole thing. So I'm going to put the 1/5 and the 10 together now in their own set of parentheses. And then I'm going to put the 1/3 and the 6 together. Now, I want to show you 2 different ways that you could multiply this together. I'm actually going to show you a shortcut. So the longer way to do this would be to just multiply straight across. So remember, this is like a 10 over 1. So if I multiply this little cluster together, this would be 10 over 5. And then this guy here, so that 6 I know is over an invisible 1. So now I can multiply straight across. So 1 times 6 is 6. 3 times 1 is 3. So I'm left with this, and then I still have to simplify. So this becomes 2 times 2, so all of this equals 4. Okay, so I want to just take a jump back and show you just a quicker way to do this, another way you could think about this. So let me clear this out. So here's a different way to think about this that's a little bit faster. So when I notice that the denominator will divide into the whole number, I just think about doing that division. So what is 10 divided by 5? 10 divided by 5 is 2. Done. What is 6 divided by 3? So 6 over 3 is the same idea as 6 divided by 3. So that would just be 2. And so I still get 4. So that's a little mental trick. If you don't want to use that, that's totally fine, but just pointing that out. Okay, so we have one more law to discuss now. So we have the distributive law. So now I've got 3 letters, A, B, and C, and I don't have a great analogy for this, but I'm going to show you why this is really cool. Okay, so the distributive law, let's say I have A times B plus C in parentheses. So very often people think visually with the distributive law and that you will literally distribute the A like this. So you're going to do A times B and then A times C. So what will that give you? That will give you AB plus AC. And usually we think of the distributive law like this direction, but I could also flip-flop this and make the b plus c come first and then multiply that times a. And all of these things are equivalent, right? So a times b and b times a, those are the same thing. A times c and c times a, those are the same thing. So you have some flexibility in here. Okay, so here's the thing about the distributive law. Many people don't fully grasp actually how great this property is. Because think about it, if we go back to this for a moment, this is a little bit of a deviation from the order of operations. So the order of operations would normally say you have to do the parentheses first and then multiply together, but that's not what we did, right? We just multiplied straight in. So basically, the distributive law, it gives us permission to switch up how we think about the order of operations. So when would I want to do that? So let me show you a couple of examples. So here I've got examples A and B, and they're very different actually. So I want you just to kind of appreciate how different they are. So if in A, so think about what the order of operations would tell us to do. The order of operations would say that we have to subtract this first because it's inside the parentheses. And that kind of sucks because then you have to actually find like a common denominator and all that. But what I notice here is that each of these denominators divide into 10. So that's a big hint. That's a thing you're always kind of thinking about and just kind of developing your numerical awareness, or numeracy as I like to call it. So I see here that 5 will divide into 10, 2 will divide into 10. So that tells me that the fractions will actually drop out if I just distribute the 10. So I've got a little lack of room here, but this is what I'm going to do. I'm going to distribute this 10 in like this. So you may or may not be able to do this in your head. So let me just show you a nice visual representation of this. So I'm going to have 10 times 2/5, that's the first part, and then minus 10 times 1/2. And however you want to multiply that together is fine. So if you want to multiply straight across, so we'll just take 10 times 2 is 20 over 5, and then this will be 10 over 2. Or you can use that other trick I was talking about earlier. This is going to give me 4 minus 5, so this equals -1. Okay, so look at how handy this was actually. I didn't have to do anything with the common denominator. It all just kind of dropped out, right? Because again, it's because these denominators divide into 10. So you have to kind of think with the order of operations and these other laws. Now, with B we actually have options. So notice now I've got a fraction out here and then these two whole numbers, but the denominator of this will actually divide into both 3 and 9. So I could distribute, or I could save myself some work, and in this case, so what happens if I combine the 6 and the 9 first? So if I use the true order of operations and I do the parentheses first, so I get 15, and now if I multiply these together, so 2 times 15 is 30, so this will be 30 over 3, and then this just equals 10. So this actually also cut down on work. So in this case, I used the distributive property. In this case, I did not. I used the order of operations. And, you know, depending on, if you think a little bit ahead, I guess what I'm trying to say is you can save yourself a little bit of work. You'll get the same answer no matter what. It's just that these are like handy shortcuts. Okay, so why don't you pause the video here and try these two and then hit play when you're ready to see the solution. Okay, so I'm going to go ahead and distribute 20 like this for this one because I don't want to make that common denominator inside the parentheses. So 20 times 1 is 20, so this will just be 20 over 4. And then 20 times 2 is 40, so this will be 40 over 5. So this will be 5 plus 8, so that equals 13. So boom, didn't even have to worry about the common denominator here. Now, for D, notice actually 5 does not divide into 14 or 4. So you would not want to distribute this right now. You actually would want to do the parentheses first. And check out what happens if I do that. So if I take 2/5 times 10, now 5 does divide into 10, so I know this will all drop out. So if I take 2 times 10, that gives me 20. 20 over 5 equals 4. Boom, done. So once again, a case where you might want to use the distributive property, a case where you do not. And it's something that you'll get better at with practice, but you can just think a little bit ahead, I guess, when you're doing some of your calculations, just thinking about if you can make them nicer, not necessarily easier, but nicer to work with. Now, we can also use the distributive property in reverse. So what do I mean by in reverse? So we always think about the distributive property with this statement first and this statement second, but what if I just flip-flop this? So now look at what this is saying. This is saying AB plus AC. It's saying I can take the A out and then just write the B plus the C. So this is the process of factoring, actually, taking that A out from the two terms. So taking out that thing that they have in common. So just really quickly here, just to practice this. So I've got Km plus Kn. So in this case, we can see that I could really clearly pull out the K because that's what's in common in both of these. So I can pull the K out, and then I'm just left with M plus N. So that's the idea of, oh, not distributing, sorry, this should say factoring, my bad. Okay, what about this other one? So now we don't have necessarily a letter in common, but there is a number that will divide both of these terms, and that number is 5, right? So if I divide 5 out of this, so if I take 5 out of this first term, I'm just left with the x. Now, if I take 5 out, you're really dividing the 5 out. So if I divide 5 out from this, what am I left with? I'm left with 2y. So this would be how that factors. So just kind of showing another way we can think about the distributive property. Okay, so we're just about done here. There's just a few other properties that are notable that I just wanted to very quickly mention. And they're things that are so obvious in some ways, you probably don't even like really ever think about them. So I just want to talk to you about the idea of the word identity. So identity is anything that gets something back to itself. So here for addition, so the additive identity is 0, because if you add any number to 0, you still get that number. So that's what this is saying. For any number a plus 0 equals a. So 0 plus anything will equal that thing. And then for multiplication, what's known as a multiplicative identity is 1. So now using this number a times 1 will always equal just a. So anything that gets back to itself is called an identity. And then the other thing I just want to mention here, just from a terminology standpoint, is the idea of an inverse. So an inverse is anything that gets you back to the identity. So it sounds a little trickier than it is. So let's say for any number a, so the addition of the opposite is 0. So if I have a and then I add negative a to it, I will get 0. So this part here, the fact that I know I can always figure out what number to add to this original number a, what will get me to 0. This is the idea of that inverse. And then with multiplication, it's a little different. So if you have some number a, then the inverse is 1 over a. And then if you multiply these two things together, notice you get back to the multiplicative identity of 1. So those are things like you probably just use them without even thinking about it, but I just wanted to do a quick refresher of the term. And that covers it for this video, guys. So hopefully I'll see you in another one. Thanks for watching.